Hello everyone and welcome back to another video. Today we're going to discuss solutions to linear congruences. Specifically, we're going to be discussing this particular equation and how to find solutions to it. AX is congruent to B mod n. How can we find solution given a, b, and n as integers? How can we find values of x that make this congruence hold? How can we find integer solutions x to this question? And what we'll find out, I guess, when we're answering this question, the process of finding solutions to this equation is actually going to parallel a lot of our discussion of linear Diophantine equations from chapter 1 all the way back in episode 4. I know we're already at episode 12. Crazy we've made it this far. But let's actually start with an example just so that you guys can kind of understand what this problem is trying to address. So for our example, we're going to talk about the solution to this equation. 2x is congruent to 3 mod 5. Now we don't have a way of solving it yet, so the way we're going to start with this is just guess and check every single value in the canonical complete residue system mod 5. So let's try x equals 0. 2 times 0 is congruent to 0, which is not congruent to 3 mod 5. So 0 is not a solution. What about x equals 1? Well, 2 times 1 is congruent to 2, which is not congruent to 3 mod 5. So that's not a solution. Let's just add x's here. What about x equals 2? Well, 2 times 2 is congruent to 4, which is not congruent to 3 mod 5. Okay. So the next one, let's look at x equals 3. 2 times 3 is congruent to 6, but this is also congruent to 1, but that still doesn't get us back to 3. But now we can maybe see like, oh, hey, now there actually is a way of getting an odd number for multiplying 2 times something here in the congruence class. What about x equals 4? Well, 2 times 4 is congruent to 8, and there we go. 8 is congruent to 3 mod 5. So our solution here is x equals 4. But also, if we multiply 2 times negative 1, we get negative 2, which is also congruent to 3 mod 5. So there's obviously other solutions as well. So how can we find these solutions, and how can we find all of the solutions, the full list of solutions? It's not as easy as just dividing 3 divided by 2 like we would do in just simple equality. There's a little bit more to this. So let's look into this a little bit more and just go through some theorems to see where we can get. So what we're going to start with a theorem about that connects solving this directly to being able to solve a linear Diophantine equation. So let's do theorem 3.19. I feel like I have more room on the left side. Yeah, a little bit more room. Okay. So for this one, we're going to let a, b, and n be integers with n greater than 0. And then we're going to show that the linear congruence that we were discussing before has a solution if and only if there exist integers x and y such that ax plus ny equals b. So this is connecting it back to that linear Diophantine equation that we discussed all throughout chapter 1 during episode 4 of this series. So for our proof, first we're just going to define a, b, and n. They're all integers with n greater than 0. And the first thing we're going to do is prove the first direction. So we're going to basically define a solution. So we're going to let ax be congruent to b mod n. For some integer x. So by the definition of congruence, we're actually getting down to part where it's covering my face is covering it. So ax minus b equals nc for some integer c. Okay, so that's one. Thus, by theorem 3. And now what we're going to do is let y equal negative c. So ax plus ny equals b. So we have a solution to that linear Diophantine equation given here with x, and then y being equal to negative c because the difference between ax and b has to be some multiple of n. So then for the other direction, we're going to let x and y be integers, such that ax plus ny equals b. So then thus ax minus b equals negative ny. So n divides ax minus b. Nice. So then hence we have this congruence here. So this x here is actually a solution to this linear congruence. So there we go. Now we've proved both directions of this first theorem. And this gives us a direct connection between linear congruence and this linear Diophantine equation from before. Basically, what we see here is that this there's always, if the solution to the linear congruence always corresponds one-to-one with a solution to this linear Diophantine equation. So that's going to help us, especially when we're trying to figure out like what's the list of all possible solutions, how can we find these solutions. We kind of have a way of generating this. Remember from before in chapter 1 when we discussed the Euclidean algorithm for finding solutions to these linear Diophantine equations. But with that in mind, let's move on to the next theorem, because then what we're going to do next is tie it more directly to the GCD. So once again, we're going to let a, b, and n all be integers with n greater than 0. And then the equation A x is congruent to B mod n has a solution if and only if A n divides B. Okay, so then for our proof, we're going to let A, B, and n all be integers with n greater than 0, and then we're going to prove each direction of the biconditional. So we're going to let Ax be congruent to B mod n for some x that's an integer, for some integer x. Thus, by theorem 3.19, there exist integers x and y that satisfy, we need to scroll down a little bit again, Ax plus and y equals B. And then if we remember from chapter 1 what having a solution to this means about this value B, from theorem 1.48, what we have that the GCD of A and n divides B, which is what we were trying to show. And then going in the other direction, let's suppose A n divides B, so B equals A n, the GCD of A and n times C for some C. By theorem 1.40, so we're starting to see all this tie back together. AP plus NQ equals AN, GCD of AN, for some PQ that are integers. Thus, B equals the GCD of A and n times C, which is equal to, or we knew this already, but that's equal to AP plus NQ, subbing in that equation, times C, which ultimately equals APC plus NQC. And then if we let x equal PC, that means that AX minus B equals NQC. And hence, we can finish the proof, because now what we have is basically just the definition of congruence. Hence, AX is congruent to B mod n. So taking these two theorems together, what we have is a strong connection between linear Diophantine equations and the GCD, which we had before, and now we're tying that all in together with linear congruence. So now, using these connections, we can actually use the linear, or use the Euclidean algorithm to solve these linear congruences. So let's try this on a more complicated linear congruence. Because remember before, all that we had was we just used this guess and checking method. But say, for example, we wanted to solve something like for example, 24x is congruent to where is it? To 123 mod 213. How would we solve this? We're not going to go through all 213 congruence classes here, guessing and checking every single time. That's just not going to work. And it also isn't going to really necessarily give us all the answers. Well, actually, technically here, we're just trying to find one answer. But using these connections, so what do we know? From theorem 3.19, we know that if a solution exists, it means that 24x plus 213y equals 123 has a solution. So this would be the solution that we could just plug in here. We also know that if there is a solution, we'd know that the GCD of 24 and 213 must divide 123. So let's use the Euclidean algorithm to solve for the GCD and then use that to create some equation where 24a plus 213b equals the GCD of 24 and 213. And then we can scale up to get x and y and 123. Since this divides 123, we can just multiply it by whatever it would be multiplied by to get 123. And then a times that number would get us to x, and then b times that number would get us to y. So that's kind of the roadmap here that I want to follow. And then let's just go through it. I'll keep this out over here, and then we can work through this together. So what we're going to start with, we're just going to apply the division algorithm, like in the Euclidean algorithm. So 213 equals 24 times 8 plus 21. Okay, so then now we can go down to 24 equals 21 times 1 plus 3. And then that means 21 equals 3 times 7 plus 0. And using this along with basically the theorem that we proved earlier to show that the Euclidean algorithm is even possible, this shows basically that the GCD here is just 3. Because remember, the Euclidean algorithm basically says that the GCD of these two numbers is equal to one of the numbers and its remainder, so we can just kind of work our way down to get it to where we have 21 and 3, whose GCD is obviously 3. So the GCD of 213, or let's do it like this, 24 and 213, just to keep the order consistent, and 213 equals 3. Now does 3 divide 123? Well, basically just doing the thing where we add up the numbers, we get 6, and 6 is divisible by 3. But what is it actually multiplied by? Well, it's 3 times 41 gets us to 123. So using what we have up here, we can kind of back our way into a solution to this equation down here, to that one down here. So what we can do, starting with 3 equals 24 minus 21 times 1. I'm just using that there. And then backing up even further, that equals 24 minus, and 21 is just 213 minus 24 times 8. So 213 minus 24 times 8, not 0.8, sorry. times 8 times 1. And then if we just kind of factor all this out, we're going to be left with 24 times 9 plus 213 times negative 1. I believe that's right. Yes. Yep. Okay. And then you can check this on your own. I checked this earlier, and this ends up being correct. So then what we want to do next is scale this up so that we can get this equal to 123. So let's take this 41 times this whole equation. Oh, wait. Times 24 times 9 plus 213 times negative 1. Okay. So then if we do this, we get that 123 equals 24 times 369 plus 213 times negative 41. Okay. So let's just double check this quickly. Let me pull up the calculator. (24 times 369 minus 41 times 213). So yeah, we solved that. Remember before, that's what we have. So 24 times 369 plus 213 times negative 41, and that gives us 123. However, there's other ways of solving this. There's other potential solutions here. But okay, so one possible solution would be this. So we know that. So basically, this is the first solution. We know 24x is congruent to 123 mod 213 when x equals 369. So that's the first solution. But there are others. I mean, one way to do it would just be to take 369 and then subtract 213. And that's just going to be something that's equivalent to 369. And then by one of those theorems we proved earlier, this will also be a solution. Just kind of showing why that is. 24 times 156 is that, let's say we just divide it by 213, gives us 17. So minus 213 times 17 gives us our 123 again. But interestingly enough, another solution to this would be 14, which isn't even congruent to the thing from before. So that gives us 336. We subtract 213, and we're back at 123. So we have all of these other solutions, and the 14 one especially stands out because it's not even congruent to 369 mod 213. So how can we get all possible solutions? It's not going to be as simple as just saying, this is the solution, we have all of these other ones that are congruent to it. There's going to be more to it than that. So how can we find all these other solutions? And that's what we're going to concern ourselves with in this next theorem. So this next theorem is going to show us the way to find all possible solutions to this linear Diophantine equation. And actually, maybe I'll leave this part open for later, because then we can actually show why x equals 14 is a solution in the next part. Okay, so that's the next part. So next, what we're going to do is prove a theorem that shows us, that kind of just lays out everything that we need to find all these possible solutions. So the theorem, we're going to let a, b, and n, not c, all be integers with n greater than 0. Then, and this theorem is actually just a list of 3 different things. This first one is actually just a kind of a restatement of theorem 3.20. So the congruence ax is congruent to b is solvable in integers if and only if the GCD of a and n divides b, so that's 1. And then number 2 is, fleshing this out a little bit more, let x not be a solution. So if we find one solution like before, let x not be a solution to the congruence ax is congruent to b mod n. So, oh wait, no, this is, I went down to the proof accidentally. Okay. Let x not be a solution to that congruence. Then all solutions are given by x not equals, or sorry, x naught plus n over GCD of a and n times m for m equals 0, 1, 2, dot, 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 a and GCD of a and n minus 1 and 3 if ax is congruent to b has a solution, then there are exactly GCD of a and n solutions in the canonical complete residue system modulo n. Okay, so that is the statement of our theorem. And now let's just go and prove each of these steps one by one. So proof, we'll just define a, b, and n for every single problem here. And then we'll also just briefly prove number one. That's the proof for step one, because this is, I mean, it's literally the same thing. It's the congruence is solvable in integers if and only if GCD of a and n divides b. This theorem is kind of just writing out everything in one large theorem that we can reference later. But for two, now we can actually start solving more interesting things now. So for two, we're going to let x naught be a solution to ax is congruent to b mod n. So that's step one. So ax naught minus b equals nc for some c and then we're going to let y naught equals c, or negative c. So ax naught plus ny naught equals b. And then we're going to go back to theorem 1.53. The linear, oh my gosh, why does this writing pad do that? Okay, the linear Diophantine equation ax plus ny equals b is satisfied by all solutions of the form x equals x naught plus kn over a n, and y equals y naught minus k a over GCD of a and n for k as an integer. Moreover, every solution is of this form. Okay. So continuing on, we're going to note here, just kind of based on this logic from before, once we have a solution to this linear congruence, we're always able to generate a solution to this linear Diophantine equation. So, and same thing vice versa. Once we have this linear Diophantine equation, we're always able to generate a solution to this linear congruence. That's kind of the logic that was used in our proof of theorem 3.19. So what we're going to do is note that the existence of a solution to the linear congruence is equivalent is equivalent to the existence of a solution to the linear Diophantine equation. Okay. So the list of all solutions to AX plus, or AX is congruent to mod n, is just x equals x naught plus kn over the GCD of a and n. However, for k1 equals k2 plus a and GCD of a and n, x naught equal, or x naught plus k1 and over GCD of a n equals x naught plus k2 plus GCD of a and n times n over GCD of a and n, which just equals x naught plus k2n over GCD of a and n plus n. And what that means, hence x naught plus k1n over a n GCD of a and n is congruent to x naught plus k2n over GCD of a and n. So if these k's differ by GCD of a and n, if you just add on GCD of a and n, you're going to start repeating solutions, basically, is the main point of this argument here. So using that, we can actually limit the amount of k's that we use just to the list from 0 through the GCD of a and n minus 1. Because once we get to GCD of a and n, you're just repeating solutions. It just cycles through this list of GCD of a and n solutions. Thus, reducing the solution to modulo n all solutions are given by this. Great, and then oh nice, you guys can see it. Sweet. Yeah, so that's the basic proof there. I can hide my face actually so you can see it more clearly. So that's basically that part of the proof there. So what we've shown is that this is the list of all possible solutions, all reduced into a modulo n form. So every single solution is going to be congruent to one of these numbers, basically. So that's that. And then with that, we can actually move on to part 3. And I'll just draw a line here just to kind of get us a little bit more clear of a distinction here in kind of the flow of the argument. Okay. So then for part 3, we're basically tasked with showing that if there is a solution, then there are exactly GCD of A and N solutions in the canonical complete residue system modulo N. And remember, the CCRS modulo N is just the list of numbers from 0 through N minus 1. It's just a list of N numbers where every single number is congruent to something in this list. So what we want to show is that there are exactly GCD of A and N solutions. We found within this list in the interval from x naught to x naught plus n minus 1, we found that in that interval of n numbers there are exactly GCD of A and N solutions, because 0 plus GCD of A and N minus 1. That's a list of, what is that? Sorry, there was some weird app that popped up. That's okay. So we found that this list is exactly a GCD of A and N long, so that means there's that many solutions in that interval. But now we want to convert that to the canonical complete residue system mod N. And I'm kind of hinting at the way that I'm going to prove this. We're going to basically the point is that interval of x naught through x naught plus n minus 1, that is a complete residue system. And we've shown that these are the exact solutions. This list of GCD of A and N numbers, those are the exact solutions within that interval. That interval is a complete residue system. So that shows us that in the canonical complete residue system, that's exactly how many solutions there are as well. So let's lay that out and make it a little bit more explicit. I didn't give myself a ton of room to work with, but that is all good. So for 3, that's basically what we're going to show. So we're going to start by letting x naught be a solution. Okay, it's a solution to that congruence. And then by part 2, all solutions to the congruence are congruent to one element in the set A equals x naught plus n over GCD of A and N times m, where m equals 0, 1, 2, ... GCD of A and N minus 1. Okay, so that's that. And then note that for each A in this set, x naught is between A, so A is between x naught and x naught plus n minus 1. And we don't need an ellipsis there, that's fine. So no two elements differ by a multiple of n, since the interval is of length n minus 1. Okay, so that's 1 point. Thus, no two elements of A are congruent. Which means each is congruent to a distinct element in the CCRS mod n. And that means, so what we're also going to do actually quickly is note that no other element in the CCRS is congruent to an element of A, so no other element is a solution, basically. Okay, thus the list of solutions in CCRS mod n is exactly the list of elements of the CCRS mod n that correspond to distinct elements in A. That correspond to distinct solutions in A. Since A equals GCD of A and N, this means there are exactly GCD of A and N solutions in, and now I'm covering it up, the CCRS mod n. And that is our proof. And that basically shows us what our theorem is. So we know that now, basically, that there are exactly GCD of A and N solutions in the complete canonical residue system modulo N. So how does this apply to what we were talking about before? So we know that, so now we have ways of generating other solutions and also ways of generating all the solutions. So in this case, let's actually just find the canonical complete residue system modulo and the solutions that are in that. So 14 is 1, but we haven't explained why that is. We need to find 3 solutions that are between 0 and 213. So the one solution we were actually able to come up with before, so this will be our x naught, is 369. And using this, we know that if we add or subtract this factor, so n over GCD of A and N, if we can add and subtract that, we will get ourselves other solutions. So this is 213 divided by 3. I haven't actually done this part of the video yet, so that's just going to be 71. I think that's right. Yeah, that's right. Okay, so that's just going to be 71. So then 369 minus 71. And this is going to start getting us our other solutions that are within the canonical complete residue system. So it's 8, 16, 2, and this is 9, 298. That doesn't get us there yet. So 7, 227, is that another solution? Yeah, that gets us even closer. So then subtract 71 again. So then it's 6. And then, sweet, okay, this will get us there. 12, and then 1, so 156. That's one of our solutions. And if we just keep going, subtracting this, we get 15 minus 7, 85 minus 71, and that'll get us to 14. So our solutions are CCRS mod 213 solutions are 14, 85, and 156. And then everything that is congruent to one of these solutions is going to give us another solution to this potential equation, or to this linear congruence here. So using this theorem, we're actually able to, so starting with the Euclidean algorithm, we're able to come up with one solution, and then using that along with this fact, and also technically in the theorem it says just add it, but technically the way this will work is if you subtract 71 each time, that's also going to get you to other solutions. This is just saying this will give us all the solutions if we just take whatever arbitrary number that is, just add, in this case 71, add 71 as many times as the GC would be, add it 3 times to the solution you came up with, and then you can reduce it back down to the CCRS after that. It's kind of the more general approach that they used, but here it made more sense just to continually subtract 71, and that's gonna end up getting you to the same solutions anyways. But yeah, so those are the 3 solutions to this linear congruence, and this actually exhausts all of the possible solutions. Every single number that is congruent to one of those 3 numbers will solve that equation, and that all comes from the Euclidean algorithm that we developed with theorem 3.19 and 3.20, and then just this additional way to iterate to all the solutions that we've developed in Theorem 3.24. So what I would recommend now, if you want to learn this a little bit better, is just continue trying to apply this to other possible equations here. And let's just zoom out and see what all that we've done today. So yeah, what I would do with this, you can actually start applying this to any sort of equation that you could come up with. Now, some of them won't work. Some of them, like, remember the condition in Theorem 3.20. Sometimes the stuff that you come up with is not going to have a solution if the GCD doesn't divide B. But I mean, if you come up with two relatively prime things, there will be a solution to any possible equation. Like how before we had 2 and 5, like you could come up with any number in the CCRS of 5 that would work with 2x there. So with that being said, yeah, I'd recommend you go and practice this. But that's all that I have for this video. So what I'll do now is open it up to the comment section. I hope you guys enjoyed watching this video. Not as many theorems today, but it feels like I'm always taking right around 1 hour to make these videos and filling up the whole page. So yeah, so I hope you enjoyed the video. Post it later today, and yeah, hope to see you guys next week in the next video. And if you like the video, go down and hit the like button. If you want to be notified of more content coming up from me, go hit the subscribe button down below. There's also a Patreon link down below as well. If you feel compelled to donate to me, I would really appreciate that as well. I'm putting in a lot of time just making these videos, prepping for all this stuff. So I would appreciate any money you wanted to throw my way. Also, there's a Discord down below that you can join and ask questions. We can discuss things, and I'll try to be more active. But yeah, that's that. And then with all that in mind, thank you all for watching, and I hope to see you all in the next video. Peace.